Tonight, we're going to look at something you've seen 1,000 times without realizing what you were actually looking at. The brightest star in the night sky, Sirius. Most people glance up, see that brilliant point of light, and think they understand it. A bright star, simple, but here's what almost nobody realizes. Sirius is not just one star, it's a system. And hidden beside that blazing white light is one of the strangest, densest objects in our entire stellar neighborhood. An object so compressed that a single teaspoon of its material would weigh more than a school bus. The brightest star in your sky is keeping a secret. And once you understand what Sirius actually is, you'll never look at it the same way again. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know. If you've ever looked up at the night sky on a clear evening, particularly during the winter months if you live in the northern hemisphere, you've probably noticed one star that seems to burn brighter than everything else around it. It's not subtle, it doesn't blend in, it dominates, it sits low in the southern sky, blazing with a fierce white light that sometimes seems to flicker with hints of blue and red, especially when it's near the horizon and its light is being bent and scattered by Earth's atmosphere. That star is Sirius, and it is, without question, the brightest star in the entire night sky as seen from Earth. Now, when I say brightest star, I mean that literally. Sirius outshines every other star visible to the naked eye. It's brighter than Arcturus, it's brighter than Vega, it's brighter than Rigel or Betelgeuse in the constellation Orion. It's brighter than Canopus, which is the second brightest star. It's brighter than every single point of starlight you've ever seen. The only natural objects in the night sky that outshine Sirius are the moon, and occasionally a few of the planets when they're at their brightest, like Venus, Jupiter, and sometimes Mars during a close approach. Everything else, every star in every constellation, is dimmer than Sirius. You can find Sirius by using the constellation Orion as a guide. Orion is one of the most recognizable patterns in the sky, with its 3 belt stars lined up in a neat row. If you follow those belt stars downward and to the left, they point almost directly at Sirius. It's unmistakable once you know where to look. Sirius sits in the constellation Canis Major, the Great Dog, and because of its position in this constellation, it's often called the Dog Star. This nickname goes back thousands of years. Ancient Egyptians watched for the first appearance of Sirius in the pre-dawn sky because it signaled the annual flooding of the Nile River, which was essential for agriculture. The Romans associated the appearance of Sirius with the hottest days of summer, which they called the dog days, a term we still use today. Sirius has been one of the most important stars in human culture for millennia. It has been observed, tracked, and studied for longer than almost any other star in the sky. And that importance wasn't limited to 1 or 2 civilizations. The Egyptians didn't just casually notice Sirius, they built an entire calendar cycle around it. The first appearance of Sirius in the pre-dawn sky after a period of invisibility, an event astronomers call a heliacal rising, marked the beginning of the Egyptian New Year. They personified Sirius as the goddess Sobdet, and the star's annual return was so precisely timed with the Nile's flooding that it became the foundation of their agricultural planning for thousands of years. The Sothic cycle, a period of roughly 1,461 years, based on the drift between the Egyptian civil calendar and the true heliacal rising of Sirius became one of the most important timekeeping tools in the ancient world. No other star received this level of attention. No other star was reliable enough, bright enough, and distinctive enough to anchor an entire civilization's calendar. The ancient Greeks saw Sirius as the source of scorching heat, believing its light combined with the sun's during summer to produce the oppressive temperatures of late July and August. Polynesian navigators used Sirius as a steering star, its reliable position helping them cross thousands of miles of open ocean in outrigger canoes. The Maori people of New Zealand knew it as Taku-Ru-A, one of the most important navigational markers in their celestial traditions. Across every continent, across every era, the brightness of Sirius demanded attention. Humans couldn't ignore it. It was simply too bright, too obvious, too impossible to miss. And every culture that looked up at the sky came to the same conclusion independently. That star, whatever it was special. But here's the question that most people never stop to ask. Why is Sirius so bright? What makes this particular star outshine all the others? Is it the biggest star out there? Is it the most powerful? Is it the closest? The answer turns out to be more interesting than any of those simple explanations. And understanding why Sirius appears so bright requires understanding something fundamental about how light works across the vast distances of space. Let's start with a concept that might seem obvious but has profound implications. The brightness of a star as you see it from Earth is not the same thing as how much light that star actually produces. These are two completely different things, and confusing them is one of the most common mistakes people make when thinking about stars. Astronomers use two different terms to keep these ideas separate. The brightness you see when you look at a star from Earth is called its apparent brightness, or apparent magnitude. This is simply how bright the star looks to your eyes from where you're standing on Earth's surface. It's a measurement of observation. It tells you what you see, but it doesn't tell you what the star actually is. The other measurement is called absolute brightness, or intrinsic luminosity. This is the actual amount of light a star produces. It's the total energy output. It's not affected by how far away the star is or how much dust might be between you and the star. It's a measurement of the star itself, independent of where you happen to be when you observe it. These two concepts, apparent brightness and intrinsic luminosity, can be wildly different for the same star. A star that appears very bright in our sky might actually be a modest star that just happens to be close to us. And a star that appears faint might be an absolute monster, one of the most powerful energy sources in the galaxy, but so far away that its light is dimmed to almost nothing by the time it reaches our eyes. Think of it this way. Imagine you're standing in a dark field at night and someone holds a flashlight 10 feet away from you. The light seems bright. Now imagine someone else holds an industrial searchlight a mile away. The searchlight produces enormously more light than the flashlight, thousands of times more, but from where you're standing, the flashlight looks brighter because it's so much closer. The searchlight might even appear as just a small dot in the distance, despite being vastly more powerful. That's exactly what's happening with stars. The night sky is full of flashlights and searchlights at different distances, and your eyes can't automatically tell the difference between a nearby dim star and a distant blazing giant. They can look the same. This distinction between apparent and intrinsic brightness is absolutely critical for understanding Sirius, because Sirius's dominance of our night sky comes from a very specific combination of factors. And the most important of those factors is distance. Sirius is close, very close by stellar standards. It sits about 8.6 light years from Earth. Now, 8.6 light years is still an enormous distance by human standards. Light travels at about 300,000 kilometers per second. In 1 year, light covers approximately 9.46 trillion kilometers. So 8.6 light years works out to roughly 81 trillion kilometers. If you tried to drive there in a car at highway speed, the journey would take more than 90 million years. By any human measure, Sirius is unimaginably far away. But by the standards of the galaxy, 8.6 light years is practically next door. The Milky Way contains somewhere between 100 billion and 400 billion stars. Most of those stars are hundreds, thousands, or even tens of thousands of light years away from us. The center of the galaxy is about 26,000 light years away. Many of the bright stars you see in the night sky are hundreds of light years distant. Betelgeuse is roughly 650 light years away. Rigel is around 860 light years away. Deneb, one of the stars in the Summer Triangle, is about 2,600 light years away. Compared to these distances, Sirius at 8.6 light years is almost incomprehensibly close. It's one of the nearest stars to our solar system. Only a handful of star systems are closer, and almost all of them are dim red dwarfs that you can't see without a telescope. This closeness matters enormously because of a physical law that governs how light behaves as it travels through space. It's called the inverse square law, and it is one of the most important principles in all of astrophysics. The inverse square law says this: as light travels outward from a source, it spreads out in all directions. Imagine the light from a star expanding outward like the surface of an inflating balloon. As the balloon gets bigger, the same amount of light is spread over a larger and larger area. And the rate at which this spreading happens follows a precise mathematical relationship. If you double the distance from the light source, the brightness doesn't just drop by half, it drops to 1/4. If you triple the distance, the brightness drops to 1/9. If you move 10 times farther away, the brightness drops to 1/100th. The brightness decreases proportionally to the square of the distance. Let me make this more concrete. Suppose you have two identical stars producing exactly the same amount of light. One is 10 light years away, and the other is 100 light years away. The far star is 10 times more distant. According to the inverse square law, the far star will appear not 10 times dimmer, but 100 times dimmer. 10 squared is 100. That's a dramatic difference. Now imagine one star is 10 light years away, and another identical star is 1,000 light years away. The distant star would appear 10,000 times dimmer. Same star, same energy output, but 10,000 times fainter to your eyes because of the distance. This law has enormous consequences for how we see the night sky. It means that distance is not just a factor in how bright a star appears, it's the dominant factor. A relatively modest star that's nearby can easily outshine a vastly more powerful star that's farther away. The inverse square law doesn't just gradually reduce brightness with distance, it crushes it, it demolishes it. Every additional light year between you and a star eats away at that star's apparent brightness with ruthless mathematical efficiency. And this is exactly what's working in Sirius's favor. Sirius sits only 8.6 light years away. Most of the stars you can see in the sky are tens, hundreds, or even thousands of light years distant. That difference in distance means that even if those far-off stars are producing enormously more light than Sirius, much of that light gets spread out and diluted across the vast distance before it reaches your eyes. Meanwhile, Sirius is sitting right here in our cosmic backyard. Its light doesn't have far to travel. It arrives at Earth still concentrated, still powerful, still brilliant. But here's where it gets really interesting. Sirius isn't just close. If it were only close, it might still be outshone by stars that are even closer. The nearest star system to Earth, Alpha Centauri, is only about 4.37 light-years away, roughly half the distance of Sirius. If closeness alone determined brightness, you'd expect Alpha Centauri to dominate the night sky, but it doesn't. Alpha Centauri is a bright star, yes, but it's noticeably dimmer than Sirius. Proxima Centauri, the closest individual star to our Sun at about 4.24 light-years, is so dim you can't even see it with the naked eye. It's a tiny red dwarf, producing only a fraction of a percent of the light our Sun produces. Being close helps, but being close isn't enough by itself. Sirius is also genuinely luminous. It's not just nearby. It's a powerful star in its own right. Sirius produces about 25.4 times more light than our Sun. That's a significant amount of energy. If you could magically swap the Sun out and replace it with Sirius at the same distance, Earth would be bathed in 25 times more light. The sky would be blindingly bright. The planet would be uninhabitable. Sirius is not a small or dim star. It's a serious energy source, considerably more luminous than the majority of stars in our galaxy. So when you combine these two facts, genuine luminosity and extreme closeness, you get a star that dominates the night sky. Sirius is bright because it's genuinely bright, and it's close enough that the inverse square law hasn't had much distance to work with. The light from Sirius has only travelled 8.6 years to reach you. It hasn't been diluted across hundreds or thousands of light years of space. It arrives at Earth, still carrying much of its original intensity. Now, to really appreciate what's happening, let's compare Sirius to some other famous stars. Because when you start looking at other stars and what they actually produce in terms of raw energy, Sirius starts to seem downright modest. Take Betelgeuse, the red supergiant that marks the shoulder of Orion. Betelgeuse is one of the most luminous stars visible to the naked eye. Its intrinsic luminosity, the total amount of light it actually produces, is roughly 100,000 times that of the Sun. Let that sink in. 100,000 times the Sun's output. Sirius, by comparison, produces about 25 times the Sun's output. Betelgeuse is roughly 4,000 times more luminous than Sirius in terms of raw energy production. It's an absolute powerhouse, a stellar furnace that dwarfs Sirius in every measure of energy output. And yet, when you look up at the sky, Sirius appears brighter than Betelgeuse. Betelgeuse is a famous star, a beautiful reddish point of light in Orion, but it's not the brightest star in the sky. Sirius is... how is that possible? How can a star that produces 4,000 times more light appear dimmer? Distance. Betelgeuse sits roughly 650 light-years from Earth. Sirius sits 8.6 light-years away. Betelgeuse is about 75 times farther away, and the inverse square law is merciless. 75 times farther means the apparent brightness is reduced by a factor of 75 squared, which is 5,625. So even though Betelgeuse produces about 4,000 times more light than Sirius, that light has to travel 75 times farther to reach us. and the inverse square law reduces its apparent brightness by over 5,000 times. The distance more than cancels out the extra luminosity. And so Sirius, the relatively modest star that happens to be right next door, appears brighter in our sky than a supergiant that could illuminate a small galaxy. Now let's look at Rigel, the bright blue-white star that marks Orion's foot. Rigel is a blue supergiant and its luminosity is staggering. It produces roughly 120,000 times the light of our sun. That's even more luminous than Betelgeuse. Rigel is one of the most powerful stars visible to the naked eye. If you placed Rigel where Sirius is, only 8.6 light-years away, it would be so brilliant that it would cast sharp shadows on Earth at night, brighter than the full moon by a significant margin. But Rigel is about 860 light-years away, 100 times farther than Sirius. The inverse square law reduces Rigel's apparent brightness by a factor of 10,000 compared to what it would be at Sirius's distance. And so Rigel, despite being nearly 5,000 times more luminous than Sirius, appears as just another bright star in Orion. Impressive, but not the brightest. The most dramatic example might be Deneb, the brightest star in the constellation Cygnus, and one of the vertices of the Summa Triangle. Deneb is a true monster. Its luminosity is estimated at roughly 200,000 times that of the Sun. Some estimates put it even higher. Deneb produces so much light that if it were placed at the same distance as Sirius, it would be dazzlingly bright, almost painful to look at. It would light up the night sky like a second moon. But Deneb sits about 2,600 light-years from Earth. That is over 300 times farther than Sirius. The inverse square law reduces its apparent brightness by a factor of roughly 90,000 compared to what it would be at Sirius's distance. Deneb, one of the most luminous stars in our region of the galaxy, a star that produces 200,000 times more energy than the Sun, appears as merely a bright star among many in the summer sky. Not the brightest, not even close to the brightest, because distance has beaten it down. Let's also consider Canopus, which is the second brightest star in the entire night sky, right after Sirius. Canopus sits in the constellation Carina and is best visible from the southern hemisphere. It's about 310 light-years away and produces roughly 10,700 times the light of the Sun. That's far more luminous than Sirius, over 400 times more luminous. And yet, Canopus is still dimmer in our sky than Sirius. Once again, distance is deciding factor. 310 light-years versus 8.6 light-years. The math is relentless. These comparisons reveal something important. The brightest star in our sky is not the most powerful star in our sky, not even remotely. There are stars visible to the naked eye that produce thousands or even hundreds of thousands of times more energy than Sirius. They're stellar furnaces of almost unimaginable power. But they're far away, very far away, and the inverse square law grinds down their light across those vast distances until they appear as ordinary points of light, each one seemingly just another star among thousands. Sirius occupies a very particular sweet spot. It's luminous enough to be genuinely impressive, producing about 25 times the light of the Sun, which puts it well above the average star. But more importantly, it's close enough that the inverse square law hasn't had time to erode much of that light. 8.6 light-years is a tiny distance by galactic standards. Most stars in the Milky Way would give almost anything to appear as close to Earth as Sirius does. That proximity, combined with genuine luminosity, is what makes Sirius the champion of the night sky. And here's something worth considering. If you could somehow move Sirius to where Deneb is, about 2,600 light years away, Sirius would be completely invisible to the naked eye. It would be far too dim to see without a telescope. A star that currently dominates the night sky, the brightest point of light you can see after the sun and moon, would simply disappear. Vanish. That's how much distance matters. The star you know as the brightest in the sky would become nothing if you simply moved it farther away. The star itself wouldn't change at all. Same mass, same temperature, same energy output, but you would never know it was there. Conversely, if you move Deneb to where Sirius is, bringing that luminous giant within 8.6 light years of Earth, it would shine brighter than the full moon. Night would not be truly dark anymore. You could read a book by Deneb's light alone. The star would cast visible shadows. It would transform the night sky into something unrecognizable. A sky dominated by a single blinding point of light that made every other star seem dim by comparison. Same star, same output, but astronomically closer. And the inverse square law would work in its favor rather than against it. This thought experiment shows you something fundamental about the night sky. What you see when you look up at the stars is not a straightforward picture of what's out there. It's a heavily distorted image, warped and shaped by distance. The brightest stars in the sky are not necessarily the most powerful. The dimmest stars are not necessarily the weakest. Distance is the great equalizer and the great deceiver, making nearby stars look brighter than they deserve, and distant giants look dimmer than they should. Sirius appears as the brightest star, not because it's the most luminous star in our neighborhood. It appears brightest because it strikes the perfect balance between genuine luminosity and extreme proximity. It's a star that is both intrinsically impressive and cosmically close, and that combination, luminosity plus closeness, is surprisingly rare. Most of the nearest stars to Earth are dim red dwarfs, invisible to the naked eye, and most of the truly luminous stars in the galaxy are hundreds or thousands of light years away. Sirius is one of the very few stars that manages to be both reasonably powerful and remarkably close at the same time. The ancient Greek astronomer Hipparchus, who lived around 190 to 120 before the Common Era, was one of the first people to systematically catalogue the brightness of stars. He ranked them on a scale from first magnitude, the brightest, to sixth magnitude, the faintest visible to the naked eye. Sirius naturally was classified as a first magnitude star, but modern astronomers realized that the old magnitude system didn't capture the full range of stellar brightness. They refined the system using precise instruments. And on the modern scale, Sirius has an apparent magnitude of negative 1.46. The more negative the number, the brighter the object. For comparison, Canopus, the second brightest star, has an apparent magnitude of negative 0.74. That might seem like a small numerical difference, but the magnitude scale is logarithmic. Each step of one magnitude represents a brightness difference of about 2.5 times. So the gap between Sirius and Canopus is actually significant. Sirius is almost twice as bright as the second brightest star in the sky. No other star comes close to matching this apparent brightness. Sirius stands alone at the top of the list, the undisputed king of the stellar sky as seen from Earth. And now you know why. Not because it's the biggest, the hottest, or the most powerful star out there, but because it's a genuinely luminous star sitting at a distance so close that its light reaches us with remarkable intensity. It's a product of real physics, real distance, real luminosity, and the relentless mathematics of the inverse square law. But here's the thing. Everything we've discussed so far treats Sirius as a single bright point of light. One star, one source, and for thousands of years, that's exactly what people assumed it was. Just one brilliant star hanging in the constellation of the Great Dog. But Sirius is hiding something. Something that wasn't discovered until the 19th century. Something that transforms our understanding of what this system actually is. Because Sirius is not just one star, it's a system. And the story of what astronomers found when they looked more closely at the brightest star in the night sky is stranger, more violent, and more fascinating than anything you'd guess from looking at that simple, bright point of light. So now we know why Sirius dominates the night sky. It's a combination of genuine luminosity and remarkable closeness. The inverse square law of light does the rest. But knowing why something appears bright is only half the story. The other half is understanding what you're actually looking at. And when it comes to Sirius, what you're looking at is far more interesting than a simple, bright point of light. Let's talk about what Sirius A actually is in physical terms. Because when you dig into the numbers, when you examine this star the way a physicist or an astrophysicist would examine it, you find something that reveals a great deal about how stars work and why the universe looks the way it does. Sirius A is what astronomers call a main sequence star. That term refers to a specific phase in a star's life, the long stable period during which it generates energy by fusing hydrogen into helium in its core. This is the same process that powers our sun. The sun has been doing this for about 4.6 billion years, and it will continue for roughly another 5 billion years before it exhausts its hydrogen fuel and begins to die. Main sequence stars are in the prime of their lives. They're stable, predictable, and long-lived relative to the more dramatic phases of stellar evolution. And Sirius A is firmly in this stage of its existence. But while Sirius A and the Sun are both main sequence stars, they are not the same kind of main sequence star. They differ in mass, size, temperature, luminosity, color, and lifespan. And those differences, which stem almost entirely from one single factor, mass, reveal one of the most elegant and powerful relationships in all of astrophysics. Let's start with mass, because mass is everything when it comes to understanding a star. Mass determines a star's temperature, its luminosity, its size, its color, its lifespan, and ultimately how it will die. If you know a star's mass, you can predict nearly everything else about it. Mass is the single most important property of any star. Sirius A has a mass of approximately 2.02 times the mass of our Sun. That might not sound like much. Twice the mass of the Sun. You might expect a star that's twice as heavy to be roughly twice as bright, or roughly twice as large, roughly twice as hot. But that's not how stars work. Not at all. The relationship between mass and luminosity in main sequence stars is dramatically nonlinear. It follows what physicists call the mass-luminosity relationship, and the consequences of this relationship are staggering. For main sequence stars, luminosity scales roughly as mass raised to the power of 3.5 to 4. This means that if you double a star's mass, you don't double its luminosity. You increase it by a factor of roughly 11 to 16 times. If you triple the mass, luminosity increases by roughly 46 to 81 times. The relationship is steep, savage, and it has profound consequences for everything about a star's existence. Sirius A has about twice the Sun's mass, and its luminosity is about 25.4 times greater than the Sun's. This fits the mass-luminosity relationship almost perfectly. A star only twice as heavy as the Sun produces more than 25 times as much light. That's an extraordinary amplification. You add a relatively modest amount of extra mass, and the star's energy output skyrockets in response. Why does this happen? It comes down to what's happening in the core. A more massive star has a stronger gravitational pull on its own material. This stronger gravity compresses the core more tightly, raising the temperature and pressure at the center. Higher core temperatures mean that nuclear fusion reactions proceed much more rapidly. The hydrogen nuclei, the protons, are moving faster, colliding more frequently, and fusing at a much higher rate. More fusion means more energy released per second, and that energy has to go somewhere. It radiates outward, making the star far more luminous, so Sirius A's core is hotter, denser, and more active than the Sun's core. The fusion reactions are burning through hydrogen at a much faster rate. The star is producing energy at a pace that far exceeds what you would expect from a simple doubling of mass. It's running its engine harder, burning hotter, and pouring out light and energy at 25 times the Sun's rate. Now let's talk about temperature. The surface temperature of a star is directly related to its mass and energy output, and it determines the star's color. Our Sun has a surface temperature of about 5,778 Kelvin. At this temperature, the Sun emits light that peaks in the yellow-green part of the visible spectrum, though we perceive it as white or yellowish-white. Astronomers classify the Sun as a G2 main sequence star, a yellow dwarf. Sirius A is hotter. Its surface temperature is approximately 9,940 Kelvin. That's roughly 72% hotter than the Sun's surface. This higher temperature shifts the peak of Sirius A's light output towards shorter wavelengths, into the blue-white part of the spectrum. When you look at Sirius in the night sky, that bright white light with hints of blue is not an illusion. It's a direct consequence of the star's surface temperature. Sirius A burns hotter than the Sun, and the color of its light tells you so. Astronomers classify Sirius A as an A1 main sequence star. The letter A indicates it's in the A spectral class, which covers stars with surface temperatures between about 7,500 and 10,000 Kelvin. These are hot stars, significantly hotter than the Sun, but not as extreme as the blue O-type and B-type stars that can reach surface temperatures of 30,000 Kelvin or more. Sirius A sits comfortably in the upper range of normal main sequence stars. It's hot, but not outrageously hot. Powerful, but not extreme. It occupies a position on the stellar spectrum that makes it genuinely impressive, without pushing into the territory of the rare, ultra-luminous supergiants. What about physical size? Sirius A has a radius of approximately 1.71 times the radius of the Sun. The Sun has a radius of about 696,000 kilometers, so Sirius A has a radius of roughly 1,190,000 kilometers. If you could place Sirius A and the Sun side by side, Sirius A would clearly be the largest star, but not overwhelmingly so. It's about 71% wider. In terms of volume, since volume scales with the cube of the radius, Sirius A has a volume roughly 5 times that of the Sun. Still not enormous by stellar standards, but genuinely bigger. To really understand what this means, let's place Sirius A in context by comparing it to the full range of star sizes that exist in the universe. Because stars come in an astonishing variety of sizes, and where Sirius A sits in that range tells us a lot about what kind of star it is. At the bottom end of the scale are the red dwarfs. These are the smallest, coolest, and dimmest main sequence stars. They're also by far the most common type of star in the galaxy. About 70% of all stars in the Milky Way are red dwarfs. Proxima Centauri, the nearest star to our solar system at 4.24 light-years away, is a red dwarf. It has a mass of only about 12% of the Sun's mass, and a radius of roughly 14% of the Sun's radius. Its surface temperature is only about 3042 Kelvin, less than a third of Sirius A's surface temperature. And its luminosity is pathetically small by comparison. Proxima Centauri produces only about 0.0017 times the Sun's luminosity. That's roughly 1/600th of 1% of the Sun's output. You'd need almost 15,000 Proxima Centauris burning together to match the light of Sirius A. And yet, Proxima Centauri is our nearest stellar neighbour. It's right there, less than half the distance of Sirius, and you can't see it without a telescope because it's so dim. Other nearby red dwarfs tell the same story. Barnard's star, about 6 light-years away, produces roughly 0.0035 times the Sun's luminosity. Wolf 359, about 7.9 light-years away, produces about 0.001 times the Sun's luminosity. Ross 128, about 11 light-years away, is similarly dim. These are the typical stars of our galaxy. Small, cool, faint, and incredibly long-lived. They burn their fuel so slowly that they'll keep shining for trillions of years, far longer than the current age of the universe, but they'll never be visible to the naked eye from any significant distance. They're the quiet background stars of the galaxy, doing their work in obscurity. Sirius A is nothing like these stars. At 25 times the Sun's luminosity, Sirius A outshines these red dwarfs by factors of 10,000, 20,000, or more. It's a fundamentally different kind of star, operating at a completely different energy level. The gap between Sirius A and a typical red dwarf is like the gap between a roaring bonfire and a candle flame. They're both producing light and heat, but the scale is entirely different. Moving up from the red dwarfs, you reach stars like our Sun. The Sun is a respectable, middle-of-the-road star. It's more massive, hotter, and more luminous than the red dwarfs, but far less extreme than the blue giants and supergiants. Sirius A sits above the Sun in every important measure. More massive, hotter, larger, more luminous. The Sun is a solid, dependable star, but Sirius A is a step up in virtually every category. Stars similar to Sirius A in the A spectral class include Vega, which has a mass about 2.1 times the Sun's, a surface temperature of about 9,600 Kelvin, and a luminosity of about 40 times the Sun's output. Fomalhaut is another A-type star with a mass about 1.92 times the Sun's and a luminosity of roughly 16.6 times the Sun's output. These stars form a class of bright, hot, blue-white main sequence stars that are significantly more impressive than the Sun, but still well within the normal range of stellar properties. Sirius A is one of the brightest and best-known members of this class. Now, above the A-type stars, you start entering the realm of the truly massive. B-type stars have surface temperatures between 10,000 and 30,000 Kelvin and luminosities that can reach tens of thousands of times the Sun's output. Rigel, the bright star in Orion, is a blue supergiant of spectral type B. It produces roughly 120,000 times the Sun's luminosity. Its mass is about 21 times the Sun's. Rigel operates on a completely different scale from Sirius A. It's hotter, far more massive, and enormously more luminous. And then there are the O-type stars, the rarest and most extreme. These blue giants can have surface temperatures exceeding 40,000 Kelvin and luminosities exceeding 1,000,000 times the Sun's output. These are the most luminous stars in the universe. They're also the rarest, making up less than 0.0003% of all main sequence stars. You could search through 100,000 stars and not find a single O-type star. They're extraordinarily uncommon. At the opposite extreme from the main sequence entirely are the red supergiants. These are stars that have left the main sequence, exhausted the hydrogen in their cores, and swelled to enormous sizes. Betelgeuse, one of the most famous red supergiants, has a radius roughly 764 times that of the Sun. If you placed Betelgeuse where the Sun is, its surface would extend past the orbit of Mars and possibly reach the asteroid belt. Its volume is so immense that you could fit hundreds of millions of suns inside it. Betelgeuse is a dying star, bloated and unstable, nearing the end of its life. An even more extreme example is VY Canis Majoris, one of the largest known stars. Its radius is approximately 1,420 times that of the Sun. If placed at the center of our solar system, its surface would extend past the orbit of Jupiter and approach Saturn. The volume of VY Canis Majoris is so vast that roughly 3 billion suns could fit inside it. These stars are monsters, swollen remnants of massive stars entering the final stages of their evolution. Compared to these titans, Sirius A is compact. At 1.71 solar radii, it barely registers on the scale of the largest stars. Betelgeuse has a radius about 447 times larger than Sirius A. VY Canis Majoris is about 830 times larger. These are differences so extreme that they almost defy comparison. If Sirius A were a marble, Betelgeuse would be a structure roughly the size of a 4-story building, and VY Canis Majoris would be larger still. But size isn't everything. And this is an important point that often gets lost when people compare stars. The red supergiants are enormous, yes, but they're also incredibly diffuse. Their outer layers are so thin, so spread out, that in some cases the gas at the surface of a red supergiant is less dense than what we'd consider a laboratory vacuum on Earth. These stars are puffed up, swollen, bloated. Their enormous size doesn't mean they contain proportionally more mass. Betelgeuse, despite being hundreds of millions of times the Sun's volume, has only about 15 to 20 times the Sun's mass. Most of that volume is near empty space, gas so thin it's practically nothing. Sirius A, by contrast, is dense and compact. Its mass is packed into a much smaller volume. The matter inside Sirius A is under extreme pressure, especially at the core, where temperatures reach roughly 22 million Kelvin. That's the temperature needed to sustain the proton-proton chain and the carbon-nitrogen-oxygen cycle that powers the star. These nuclear reactions convert mass into energy according to Einstein's famous equation, releasing photons that slowly work their way outward through the star's interior over the course of tens of thousands of years before finally escaping from the surface as the brilliant white light we see from Earth. Now, Here's something that might sound counterintuitive, but is one of the most important facts in stellar astrophysics. More massive stars live shorter lives. This seems backward at first. You'd think a star with more fuel would last longer, just as a bigger gas tank lets a car drive farther. But stars don't work like cars. A more massive star doesn't just have more fuel, it burns that fuel at a spectacularly faster rate. The mass-luminosity relationship we discussed earlier explains why. A star twice as massive doesn't produce twice the energy. It produces roughly 11 to 16 times the energy. It's burning through its fuel reserves at an enormously accelerated rate. Our Sun has a total main sequence lifespan of roughly 10 billion years. It's about 4.6 billion years into that lifespan right now. So it's roughly middle-aged. It has plenty of fuel left, and will continue shining steadily for another 5 billion years or so before it begins to exhaust its hydrogen and evolve off the main sequence. Sirius A is a different story. Despite being only twice as massive as the Sun, its dramatically higher luminosity means it's consuming its hydrogen fuel far more rapidly. The estimated total main sequence lifespan of Sirius A is roughly 1 billion to 1.2 billion years. That's only about 1/10 to 1/8 as long as the Sun's lifespan. Sirius A burns brighter, but it pays for that brightness with a much shorter life. Current estimates suggest that Sirius A is roughly 200 to 300 million years old. This means it's already used up a significant fraction of its main sequence lifespan. But it still has several 100 million years to go before it begins to evolve. It's not in any danger of dying anytime soon. But compared to the Sun, which will last for 10 billion years in total, Sirius A's lifespan is brief. In the time it takes the Sun to live out its full life, 10 stars like Sirius A could be born, live, and die. This inverse relationship between mass and lifespan has profound consequences for the galaxy. The most massive O-type stars, with luminosities millions of times the Sun's, may live for only a few million years. They blaze with incredible intensity and then die in spectacular supernova explosions, scattering their material across space. Meanwhile, the smallest red dwarfs, with luminosities less than 1,000th of the Sun's, will burn steadily for trillions of years. Long after the last massive star in the galaxy has exploded and faded, the red dwarfs will still be glowing, dim but persistent, outlasting everything else. Sirius A falls somewhere in between. It's not one of the ultra-short-lived massive stars, but it's not a long-lived red dwarf either. It's a star that lives for about 1 billion years, which is long enough for interesting things to happen in its vicinity, but short enough that its time on the main sequence is limited. Planets orbiting Sirius A, if any exist, would have far less time for the kind of slow biological evolution that occurred on Earth. Life on Earth took roughly 3.8 billion years to go from simple, single-celled organisms to complex multicellular creatures. Sirius A's entire main sequence lifespan is only about 1 billion years. There simply wouldn't be enough time for the kind of slow, gradual evolution that produced complex life on Earth. Let's put Sirius A on the Hertzsprung-Russell diagram to see where it fits among all known stars. The HR diagram is one of the most important tools in stellar astrophysics. It's a plot that shows stars according to their luminosity and surface temperature. When you plot thousands of stars on this diagram, a striking pattern emerges. Most stars fall along a diagonal band running from the upper left, hot and luminous, to the lower right, cool and dim. This band is the main sequence, the region where stars spend most of their lives fusing hydrogen into helium. The Sun sits roughly in the middle of the main sequence. It's an average star in an average position. Sirius A sits above and to the left of the Sun on the HR diagram. It's hotter, so it's farther to the left, and it's more luminous, so it's higher up. It occupies a position that tells astronomers immediately what kind of star it is. A hot, luminous, blue-white main sequence star, more massive and more powerful than the Sun, but not yet in the territory of the rare blue supergiants that dominate the upper left corner of the diagram. Above the main sequence on the HR diagram, you find the giants and supergiants. These are stars that have left the main sequence, exhausted their core hydrogen, and expanded to enormous sizes. Betelgeuse sits in the upper right corner of the HR diagram, extremely luminous, but relatively cool, which gives it that distinctive red color. Rigel sits in the upper left, extremely luminous and extremely hot, blue-white in color. These stars have evolved off the main sequence and are in the late stages of their lives. Below the main sequence, you find the white dwarfs. These are the compact remnants of dead stars. Small, hot, but very dim because of their tiny size. They sit in the lower left corner of the HR diagram. We'll have much more to say about white dwarfs later, because Sirius has a very direct connection to one of them. But for now, just note their position. They're small, faint, and fundamentally different from main sequence stars. The HR diagram shows clearly that Sirius A is in the prime of its life. It's on the main sequence, fusing hydrogen, stable, and luminous. It's not a dying star, and it's not a stellar remnant. It's a fully active, fully functioning star, operating at a level of energy output that exceeds the Sun by a factor of 25. Let me also address something that occasionally comes up when people discuss Sirius. Some sources describe it casually as just a bright nearby star, as if its fame comes entirely from proximity and there's nothing intrinsically special about it. This is misleading. Sirius A is not just close, it's genuinely impressive in its own right. A luminosity of 25 times the Sun's output puts it well above the vast majority of stars in the galaxy. Remember, about 70% of all stars are dim red dwarfs with luminosities less than 1% of the Sun's. Sirius A outshines the Sun by a factor of 25. It outshines the average star in the galaxy by a factor of several thousand or more. If you dropped Sirius A into a random spot in the Milky Way, it would be one of the brightest stars in its local neighborhood, almost regardless of where you placed it. Sirius A is also massive enough to end its life in an interesting way. When it eventually exhausts its hydrogen fuel, it will expand into a red giant, swelling to many times its current size. Its outer layers will eventually be expelled into space, forming a planetary nebula, a beautiful shell of glowing gas illuminated by the hot core left behind. That core will contract and become a white dwarf, slowly cooling over billions of years. This is the fate that awaits all stars in Sirius A's mass range, roughly 0.8 to 8 solar masses. They don't explode as supernovae. They shed their outer layers gently and leave behind compact remnants. And this brings us to something remarkable, because when we talk about Sirius A eventually becoming a white dwarf in the distant future, we need to recognize that it's not the first star in this system to face that fate. The system has already experienced this process. Another star, one that was once even more massive and more luminous than Sirius A, has already lived, died, and collapsed into a white dwarf. that dead star is still there, orbiting Sirius A right now, hidden in the glare of its brilliant companion. And its story is one of the most extraordinary in all of stellar astronomy. But before we explore that companion, let's take one more moment with Sirius A. Because understanding what it is, understanding its mass, its temperature, its luminosity, its position on the HR diagram, its expected lifespan, this is essential groundwork. Sirius A is not a generic star. It's a specific kind of star with specific properties that place it firmly in the upper tiers of main sequence stellar performance. It's a star that produces 25 times the energy our Sun produces. A star with a surface temperature approaching 10,000 Kelvin. A star that burns blue-white, compact and fierce, sitting less than 9 light-years from Earth. It's genuinely impressive, not because of hype or historical reputation, but because of the physics. The numbers don't lie. And yet, for all its power, for all its luminosity and mass and heat, Sirius A is only half the story of this system. Because right next to it, separated by a distance roughly comparable to the distance between the Sun and Uranus, is an object so strange, so dense, so fundamentally different from Sirius A that it forced astronomers to rethink what they understood about how stars live and die. That object, tiny and faint and almost invisible next to the blinding light of its companion, is one of the most remarkable stellar remnants ever discovered. And the way it was found, decades before anyone ever laid eyes on it, is a story that begins not with light, but with gravity. The story of Sirius B begins not with a telescope, but with a wobble, a tiny, almost imperceptible irregularity in the motion of the brightest star in the sky. And the person who noticed it was a German astronomer and mathematician named Friedrich Bessel. Bessel was one of the most precise observational astronomers of the 19th century. He was meticulous, exacting, and obsessed with accuracy. In the 1830s, he began carefully tracking the position of Sirius against the background of more distant stars, measuring its movement across the sky with extraordinary precision. Stars aren't fixed in space. They move. Our Sun moves. Every star in the galaxy is in motion, following its own path through the Milky Way under the influence of gravity. From Earth's perspective, this motion causes nearby stars to slowly shift their positions against the more distant background stars over the course of years and decades. This movement is called proper motion, and Sirius has a significant proper motion because it's so close to us. It moves across the sky at a rate that's measurable with good instruments over just a few years. But Bessel noticed something strange. Sirius wasn't moving in a straight line. It was wobbling. The path it traced across the sky wasn't the smooth, linear track you'd expect from a single star moving through space. Instead, it followed a gently wavy line, oscillating back and forth around its average position. The wobble was small, but Bessel's measurements were precise enough to detect it clearly. Something was pulling on Sirius, tugging it back and forth in a regular, periodic rhythm. In 1844, Bessel published his conclusion. He proposed that Sirius had an unseen companion, a second object orbiting it, whose gravitational pull was causing the observed wobble. The two objects, Sirius and its invisible companion, were orbiting a common center of mass, and this orbital dance caused Sirius to trace a wavy path across the sky, rather than a straight one. Bessel couldn't see the companion. No one could. But the mathematics of the wobble left no other explanation. Something massive was there. hidden in the glare of the brightest star in the sky. This was a remarkable prediction. Bessel was claiming the existence of an object that no human eye had ever seen, based purely on the gravitational effect it had on another object. It was the same method that would later be used to discover Neptune, whose existence was predicted from perturbations in the orbit of Uranus before anyone spotted it through a telescope. Gravity reveals what light conceals. An invisible object can betray its presence through the pull it exerts on things we can see, but confirmation had to wait. For nearly 2 decades, astronomers searched for the companion without success. The problem was that whatever was orbiting Sirius was faint, extremely faint, and it was sitting right next to the brightest star in the night sky. Trying to spot a dim object next to Sirius was like trying to see a firefly next to a searchlight. The glare of Sirius A overwhelmed everything around it, drowning out any faint companion in its brilliance. Then, on the evening of January 31st, 1862, an American telescope maker named Alvin Graham Clark was testing a new 18.5-inch refracting telescope, one of the largest in the world at the time. He pointed it at Sirius to check the quality of the lens, and there, almost lost in the blinding glare of Sirius A, he spotted a tiny point of light. A faint star sitting close to Sirius, exactly where Bessel's calculations predicted the companion should be. This was Sirius B, the hidden companion. The invisible object that had been tugging on Sirius for millions of years, betraying its presence only through gravity, had finally been seen with human eyes. But the discovery raised more questions than it answered. Because when astronomers began to study Sirius B to measure its properties, to figure out what this object actually was, they encountered something that didn't make sense. Something that would take decades of physics to explain, and would ultimately require a revolution in our understanding of matter itself. The first problem was brightness. Sirius B was dim, extraordinarily dim. When astronomers measured its apparent brightness, they found it was roughly 10,000 times fainter than Sirius A. 10,000 times. This was a staggeringly large difference. Remember, Bessel's wobble analysis had indicated that the companion must be massive. The gravitational tug on Sirius A was substantial. You can't produce a significant wobble with a lightweight object. The math suggested the companion had a mass comparable to the Sun, but here was an object with the mass of a star producing only a tiny fraction of a normal star's light. A mass like the Sun's should produce luminosity like the Sun's, but Sirius B was producing almost nothing. It was putting out roughly 0.026 times the Sun's luminosity, about 2.6% of what the Sun produces. For something as massive as an entire star, this was absurdly dim. The second problem came in 1915, when the astronomer Walter Adams managed to measure the spectrum of Sirius B's light. Spectroscopy tells you the temperature of a star. Different temperatures produce different patterns in the light, different distributions of wavelengths. When Adams analyzed Sirius B's spectrum, he found that its surface temperature was extraordinarily high, around 25,000 Kelvin. That's more than 4 times hotter than the Sun's surface, and it's more than twice as hot as Sirius A itself. This created a paradox. Sirius B was extremely hot, but extremely dim. How is that possible? For a normal star, temperature and luminosity go hand in hand. A hotter surface radiates more energy per unit area. The Stefan Boltzmann law tells us that the energy radiated from a surface increases as the 4th power of the temperature. So a surface that's twice as hot radiates 16 times more energy per unit area. A surface 4 times hotter radiates 256 times more energy. Sirius B's surface at 25,000 Kelvin should be radiating enormous amounts of energy per unit area. Far more than the Sun's surface, far more than Sirius A's surface, and yet Sirius B was dim. The only way to reconcile a very hot surface with a very low total luminosity is if the surface area is very small. If the object radiates a lot of energy per square meter of surface, but has very few square meters of surface, the total output could be low. The math pointed to only one conclusion: Sirius B had to be tiny. When astronomers calculate the size, the result was shocking. Sirius B had a radius of only about 5,800 kilometers, roughly 0.008, 4 times the Sun's radius. That's approximately 0.92 times the radius of Earth. Let that settle for a moment. Sirius B, an object with roughly the mass of the entire Sun, was compressed into a volume approximately the size of Earth. The Sun has a radius of about 696,000 kilometers. Sirius B has a radius of about 5,800 kilometers. The Sun is roughly 120 times wider. But Sirius B has approximately the same mass as the Sun, all crammed into a sphere roughly the size of our planet. The density implied by these numbers is almost beyond comprehension. If you take the mass of the Sun, roughly 2 times 10 to the 30th kilograms, and compress it into a sphere the size of Earth, you get a density of over 1,000,000 grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Iron has a density of about 7.87 grams per cubic centimeter. The densest naturally occurring element on Earth's surface, osmium, has a density of about 22.59 grams per cubic centimeter. Sirius B has a density tens of thousands of times greater than osmium, over 1,000,000 times denser than water. This leads to one of the most frequently quoted facts about white dwarfs, and it remains staggering no matter how many times you hear it. A teaspoon of material from Sirius B, a volume of about 5 milliliters, would weigh approximately 8.5 metric tons on Earth. 8.5 tons from a teaspoon. That's roughly the weight of a loaded school bus, compressed into a volume you could balance on a spoon. A cubic meter of Sirius B's material would weigh about 1.7 billion kilograms. You could take a sugar cube-sized chunk of this star, and it would outweigh an ocean liner. When these numbers were first calculated in the early 20th century, they were met with disbelief. And not casual disbelief. The scientific community was genuinely disturbed. Arthur Eddington, one of the most prominent astrophysicists of the era, called Sirius B's density absurd. He famously wrote that a message from Sirius B would read something like this: "I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget that you could put in a matchbox." Eddington knew the measurements were correct, but he couldn't explain how such density was physically possible. This was not a minor puzzle. It was a crisis. The physics of the early 20th century simply did not have the tools to explain how matter could exist in this state. Classical physics predicted that atoms have a minimum size determined by the electron clouds around their nuclei. You could squeeze matter together, but at some point the electron clouds would resist. They'd push back. There was a flaw to how dense matter could get, and that flaw was far, far below what Sirius B required. By any classical understanding, Sirius B should not exist. The matter inside it should be physically impossible. And yet there it was, orbiting the brightest star in the sky, real and measurable, and stubbornly refusing to conform to the physics of the day. For years, Sirius B sat as an awkward anomaly. Astronomers could measure it, they could calculate its density, but they couldn't explain it. A few other white dwarfs had been identified by this time. 40 Eridani b had been recognized as unusually small and dense, and Van Manen's star was another puzzling compact object. These discoveries confirmed that Sirius B wasn't a one-off measurement error. There was an entire class of these dense, compact objects scattered through the galaxy. The problem wasn't going away, it was getting worse. The answer came from quantum mechanics, the revolutionary physics of the subatomic world that was being developed in the 1920s and 30s. In 1926, the British physicist Ralph Fowler applied the principles of quantum mechanics to the problem of white dwarf structure. He showed that the matter inside a white dwarf is held up not by thermal pressure, as in a normal star, but by something called electron degeneracy pressure. In normal matter, electrons orbit atomic nuclei in well-defined shells. The matter has structure, but inside a white dwarf, the atoms have been completely crushed. The electrons have been stripped from their nuclei and are free to move through the material. The nuclei, mostly carbon and oxygen in a white dwarf like Sirius B, are packed tightly together in a lattice, almost like a crystalline structure. And the electrons form what physicists call a degenerate electron gas. The key insight from quantum mechanics is the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state. As the matter is compressed further and further, the electrons are forced into higher and higher energy states because the lower states are already occupied. This creates an outward pressure, a resistance to further compression that has nothing to do with temperature. It's a purely quantum mechanical effect. Even if you cooled the white dwarf to absolute zero, this pressure would still be there. The electrons resist being squeezed into the same quantum states, and that resistance supports the star against its own gravity. This was a breakthrough in understanding. It explained how Sirius B could exist. The star isn't supported by the heat of nuclear fusion like a normal star. It has no fusion occurring in its core. It's not generating any new energy. It's simply a ball of incredibly compressed matter, held up against gravitational collapse by the quantum mechanical stubbornness of electrons refusing to be packed any closer together. Sirius B, the strange companion to the brightest star in the sky, had driven physics forward. An anomaly in the sky had forced a revolution in the laboratory. The universe, as it so often does, was ahead of human understanding, presenting evidence for physics that hadn't been invented yet. But this leads to a natural question. If Sirius B is a dead star, a stellar remnant with no nuclear fusion occurring in its core, where did it come from? What was Sirius B before it became a white dwarf? And the answer to this question transforms our understanding of the entire Sirius system. Sirius B is the corpse of a star that was once alive. It was once a normal main sequence star, burning hydrogen in its core, producing light and heat through nuclear fusion. It had a surface, an atmosphere, a luminosity, a color. It was a real, functioning star. And here's the part that might surprise you. It was once more massive than Sirius A is. We know this because of how stellar evolution works. Stars die in a specific order in a binary system, and the order is determined entirely by mass. The more massive a star is, the faster it burns through its fuel, and the sooner it dies. This is the mass-lifespan relationship we discussed earlier. More massive stars live shorter lives because they burn their fuel at a disproportionately faster rate. In the Sirius system, Sirius B died first. It ran out of fuel and collapsed into a white dwarf, while Sirius A was still on the main sequence, still fusing hydrogen, still very much alive. This means Sirius B must have been the more massive star originally. It had to be, because it exhausted its fuel faster. Current estimates suggest that Sirius B's original mass, when it was still a living star, was roughly 5 solar masses, 5 times the mass of the Sun. That would have made it a hot, luminous B-type star, far brighter and far more impressive than Sirius A is today. For a time, the Sirius system was dominated not by the star we see now, but by a blazing blue giant that outshone its companion by a wide margin. But that blue giant burned through its hydrogen at a furious rate. Within roughly 100 million years, it exhausted the hydrogen in its core. When a star runs out of core hydrogen, the fusion reactions that have been supporting it against gravity begin to fail. The core contracts. Hydrogen fusion continues in a shell around the core, and the outer layers of the star expand enormously. The star swells into a red giant, ballooning to many times its original size. For a star of 5 solar masses, this red giant phase would have been dramatic. The star would have expanded until it was dozens or even over 100 times its original radius. Its outer layers would have become cool and tenuous, glowing red and orange. If you could have been there, if you could have watched the Sirius system during this epoch, the sight would have been extraordinary and terrifying. Where once there had been 2 compact blue-white stars, now there was a monstrous red giant, vast and cool and distended, its outer atmosphere reaching across enormous distances. Sirius A, still a compact main sequence star, would have been partially engulfed by the swelling atmosphere of its dying companion, or at the very least, showered with material streaming outward from the giant's surface. The space between the 2 stars would not have been empty. It would have been filled with gas, streamers and filaments of stellar material being torn from the dying giant by tidal forces. Some of it spiraling towards Sirius A, some of it being flung outward into the void. The system would have looked nothing like the clean, elegant pair we see today. It would have been violent, messy, and spectacular. During the red giant phase and the subsequent asymptotic giant branch phase, the dying star shed its outer layers into space. Stellar winds, gentle at first and then increasingly powerful, stripped material from the star's surface and flung it outward. Over hundreds of thousands of years, the star lost a substantial fraction of its mass. Material that had once been part of a living star was cast into the surrounding space, forming a slowly expanding shell of gas and dust, called a planetary nebula, though such nebulae have nothing to do with planets. The name is historical, dating from a time when these round glowing shells were mistaken for distant planetary systems. That planetary nebula would have been beautiful, a glowing shell of ionized gas lit from within by the intense ultraviolet radiation of the exposed core. The proto-white dwarf at its center, greens and blues from ionized oxygen, reds from hydrogen, complex structures shaped by the interaction between the stellar wind and the surrounding medium and the gravitational influence of Sirius A, pulling the shell into asymmetric shapes. For perhaps 20,000 to 50,000 years, the Sirius system would have been surrounded by this luminous cloud, a cosmic lantern visible from neighboring star systems. Then, gradually, the nebula would have expanded, thinned, cooled, and faded. The glow would have dimmed. The gas would have dispersed into the interstellar medium, mixed with the thin material between the stars, and become undetectable. Today, hundreds of millions of years later, no trace of that nebula remains. It has been diluted beyond any hope of detection, but it was there. The evidence is Sirius B itself. After the outer layers were expelled, all that remained was the star's core. A ball of carbon and oxygen nuclei compressed to extraordinary density, no longer capable of sustaining nuclear fusion. This core, roughly the mass of the Sun but the size of Earth, was Sirius B, a white dwarf, the naked core of a dead star, slowly radiating away its residual heat into space. Today, Sirius B has a mass of approximately 0.978 solar masses, just under the mass of the Sun. But remember, the original star was roughly 5 solar masses. Where did the other 4 solar masses go? They were expelled during the red giant and planetary nebula phases. All that material, roughly 4 times the mass of the Sun, was flung into space. Some of it may have been captured by Sirius A, enriching its outer layers with heavier elements. Some of it dissipated into the interstellar medium. The planetary nebula itself has long since dispersed, spread so thin across space that it's completely undetectable today. But the evidence of this violent mass loss remains encoded in the properties of Sirius B itself, in the gap between its current mass and the mass it must once have had. This history means that the Sirius system has been through a dramatic transformation. Millions of years ago, it would have looked completely different. Instead of one bright blue-white star with a tiny faint companion, you would have seen 2 bright stars. The brighter one, the original Sirius B, would have been a blazing blue giant, far more luminous than Sirius A. Then that star would have swelled into an enormous red giant, potentially engulfing or at least dramatically affecting its companion. Material would have streamed between the 2 stars. A planetary nebula would have formed, a beautiful glowing shell of expelled gas surrounding the binary pair. And then, as the nebula faded and dispersed, the system would have settled into what we see today. One bright main sequence star and one tiny, incredibly dense remnant of a star that died long ago. The age of the Sirius system provides important context. Current estimates place the age of Sirius A at roughly 200 to 300 million years. But this age refers to Sirius A's current phase on the main sequence. The original star that became Sirius B lived and died before Sirius A reached its current state. The progenitor of Sirius B, being more massive, would have had a main sequence lifespan of only about 100 million years. After that, it would have taken a relatively brief time, astronomically speaking, perhaps a few million years, to pass through the red giant phase and collapse into a white dwarf. So the events that created Sirius B occurred over 100 million years ago. The planetary nebula bloomed and faded. The white dwarf began its long, slow cooling, and Sirius A continued burning steadily on the main sequence, now the sole active star in the system, accompanied by the cooling remains of a companion that once outshone it. White dwarfs cool very slowly. Because they're so small, they have a very small surface area from which to radiate energy, and because they're so dense, they contain an enormous amount of stored thermal energy. Even though they produce no new energy through fusion, the heat already trapped inside them takes billions of years to radiate away completely. Sirius B currently has a surface temperature of about 25,000 Kelvin, which is extremely hot. hotter than Sirius A, hotter than most main sequence stars. But Sirius B is cooling. Slowly, inexorably, it's radiating away the heat it accumulated during its life as a star. Over billions of years, it will cool from white hot to yellow, to orange to red, eventually becoming so cool and dim that it will be essentially invisible. Astronomers call this theoretical endpoint a black dwarf, a white dwarf that has cooled completely. But the universe isn't old enough for any black dwarfs to exist yet. The cooling process takes so long that even white dwarfs that formed in the very early universe are still warm and faintly glowing today. The Indian-American astrophysicist Subramanian Chandrasekhar made a crucial contribution to our understanding of white dwarfs in the 1930s. He calculated that there is a maximum mass a white dwarf can have. Beyond this limit, the electron degeneracy pressure that supports the white dwarf is no longer sufficient to resist gravity. The star would collapse further, becoming either a neutron star or a black hole. This maximum mass is called the Chandrasekhar limit, and it's approximately 1.4 times the mass of the Sun. Sirius B, at 0.978 solar masses, sits safely below this limit. Its electron degeneracy pressure is more than sufficient to hold it up against gravity. It will remain a white dwarf forever, slowly cooling over trillions of years, never collapsing further. But if a white dwarf somehow gained enough mass to push it past the Chandrasekhar limit, the consequences would be catastrophic. The electron degeneracy pressure would fail. The star would collapse. In certain scenarios, particularly when a white dwarf accumulates material from a companion star, this can trigger a thermonuclear explosion that completely destroys the white dwarf. This type of explosion is called a Type 1a supernova, and it's one of the most powerful events in the universe. These explosions are so consistent in their peak brightness that astronomers use them as standard candles to measure distances across the cosmos. They were instrumental in the discovery that the universe's expansion is accelerating. Sirius B is not currently in danger of reaching the Chandrasekhar limit. It's not actively pulling significant amounts of material from Sirius A. The two stars are far enough apart that mass transfer is not occurring at any meaningful rate. But the physics underlying the limit is important for understanding what white dwarfs are and what they're capable of. These are not inert objects. They are matter in an extreme state, held in a delicate quantum mechanical balance between gravity pulling inward and electron degeneracy pressure pushing outward. Disturb that balance, and the results can be spectacular. The discovery and study of Sirius B was pivotal in the history of astrophysics. It was one of the first white dwarfs ever identified. It forced physicists to confront the existence of matter at densities that seemed physically impossible. It demanded explanations that only quantum mechanics could provide. And it demonstrated that the universe contains objects that are fundamentally different from anything in our everyday experience. Objects where a teaspoon of material weighs over 8 tons, where the mass of an entire star is compressed into a volume the size of a planet, where matter exists in a state so extreme that it's held together not by chemical bonds or thermal pressure, but by the quantum mechanical refusal of electrons to share the same state. Sirius B sits right there in our cosmic backyard, only 8.6 light years away, one of the nearest white dwarfs to Earth, an object so dense it borders on the surreal, and it orbits silently around the brightest star in the night sky, invisible to the naked eye, hidden in the overwhelming glare of its companion, a ghost from a violent past that most people never even suspect is there. The next time you look up at Sirius on a clear winter night, remember what you now know. That brilliant point of light is not one star. It's two. One blazing with the fierce blue-white light of a powerful main sequence star. And the other, invisible to your eyes, is one of the densest objects in the known universe, the collapsed core of a star that died millions of years ago, still glowing faintly with the residual heat of its former life. The brightest star in the sky is keeping company with a corpse. And the story of how these two objects came to be bound together, the physics of their orbit, and what their relationship tells us about the nature of stars, that story still has more to reveal. Now we can finally see the full picture. We can bring Sirius A and Sirius B together and understand what the system actually is. Not a single bright star, but a gravitationally bound pair locked in an orbital dance that has been going on for hundreds of millions of years. And the mechanics of that dance, the physics of how these two profoundly different objects interact, tells us something remarkable about how the night sky really works. Sirius A and Sirius B orbit each other with a period of approximately 50.1 years. That means every half century, the two stars complete one full loop around their common center of mass. This center of mass, called the barycenter, sits closer to Sirius A because Sirius A is the more massive of the two. Sirius A has a mass of about 2 solar masses, while Sirius B has about 0.978 solar masses. So the barycenter lies roughly 2/3 of the way from Sirius B toward Sirius A, shifted toward the heavier partner, and both objects trace elliptical paths around that invisible point. The orbit is not circular, it's noticeably elliptical, with an eccentricity of about 0.59. This means the distance between the two stars changes significantly over the course of each orbit. At their closest approach, called periastron, Sirius A and Sirius B are separated by roughly 8 astronomical units. That's about 8 times the distance from Earth to the Sun, falling between Jupiter's orbit and Saturn's orbit in our own solar system. At their farthest separation, called apastron, they're about 31.5 astronomical units apart. That's roughly the distance from the Sun to Neptune. So over the course of a single 50-year orbit, the distance between these two stars swings from Jupiter to Saturn-like separations to Neptune-like separations and back again. It's a substantial orbit spanning a significant portion of a stellar system. From Earth, this orbital motion is observable but challenging. The angular separation between Sirius A and Sirius B, as seen from Earth, changes over the course of the 50-year cycle. At their widest apparent separation, they can be distinguished through a moderately powerful telescope. At their closest apparent separation, Sirius B is nearly impossible to see even with professional instruments, because it's swallowed by the overwhelming glare of Sirius A. The period around closest approach is when Sirius B effectively vanishes, hidden not by distance, but by the brilliance of its companion. Astronomers have to use extremely careful techniques, including coronagraphs that block out most of Sirius A's light and observations in X-ray wavelengths, where Sirius B is relatively brighter compared to Sirius A, to study the faint companion during these difficult periods. Since Alvin Graham Clark first spotted Sirius B in 1862, astronomers have tracked the pair through more than 3 complete orbits. That's over 160 years of continuous observation. one of the longest baselines of orbital data for any binary star system. Each orbit has refined our understanding of the system's properties. The masses of both stars, the shape and orientation of the orbit, the orbital period, all of these have been measured with increasing precision as decade after decade of positional data has accumulated. In the earliest decades after discovery, measurements were limited by the technology of the time. Visual observations through eyepieces, hand-drawn plots of the companion's position relative to the primary. But even those early observations were good enough to confirm Bessel's prediction and establish the basic parameters of the orbit. By the 20th century, photographic plates allowed more precise measurements, and in recent decades, space-based telescopes and advanced imaging techniques have pushed the precision further still. The Hubble Space Telescope has imaged the Sirius system multiple times, resolving the two stars even when they're relatively close together in their orbit. These observations have allowed astronomers to measure the mass of Sirius B to within a fraction of a percent, making it one of the most precisely characterized white dwarfs in existence. Each orbit is like a fresh experiment, a new chance to refine the numbers and test our understanding of gravitational physics in a real stellar laboratory. Think about what this system would look like if you could somehow travel there and observe it up close. If you approached from a great distance, you'd see what looks like a single brilliant white star, just as we see from Earth. As you drew closer, you'd begin to notice that the star's position shifted subtly. That faint wobble that Friedrich Bessel first detected in the 1830s. Closer still, and you'd start to resolve two separate points of light. One blindingly bright, blue-white, and dominant. The other tiny, faint, but with a subtle bluish-white glow of its own. If you could somehow park yourself at a safe distance and watch over decades, you'd see these two objects slowly circling each other. The bright one moving in a small ellipse, the faint one moving in a larger ellipse, both tracing out their paths around their shared center of gravity with the precision of a clockwork mechanism governed by Newton's laws. If you could visit a hypothetical planet orbiting at a safe distance within this system, the sky would be extraordinary. Sirius A would dominate. A brilliant blue-white sun, far more luminous than the star we orbit back on Earth. And somewhere in that sky, sometimes closer and sometimes farther depending on the orbital phase, you'd see a second star. Tiny, almost stellar in appearance, but with an eerie intensity to its light. Bluish white and far hotter than it has any right to be for something so small. That would be Sirius B. A point of light no larger than a planet, radiating with the residual heat of a star that died millions of years ago. Two suns in the sky, one blazing with the full power of a main sequence hydrogen fusion, the other a ghostly remnant, slowly fading into darkness over billions of years. Now let's think about what this system's history tells us. Because the story of the Sirius system is not a simple story of two stars being born together and quietly orbiting each other forever. It's a story of transformation, violence, mass loss, and a dramatic reversal of roles. Hundreds of millions of years ago, when the system was young, the situation was reversed. The star we now call Sirius B was the dominant member. It was roughly 5 times the mass of the Sun, a hot B-type star blazing with enormous luminosity. Sirius A, at about 2 solar masses, was its less impressive companion. If any ancient alien astronomer in a neighbouring star system had observed the pair, they would have noted the brighter star as the primary and might not have paid much attention to the smaller companion at all. Sirius B, in its former life, was the main attraction, but that massive star consumed its hydrogen fuel at a ferocious rate. Within roughly 100 million years, its core hydrogen was exhausted. The star evolved off the main sequence, swelling into an enormous red giant. During this phase, the system would have been a striking sight. A massive red giant, perhaps dozens of times the radius of the current Sirius A, glowing red and orange, accompanied by a smaller blue-white companion. The red giant would have dominated the visual appearance of the system, dwarfing its partner in physical size even as its surface cooled and its color shifted. Then came the mass loss. As the giant star shed its outer layers, enormous quantities of material were flung into space. Stellar winds carried gas outward in all directions. A planetary nebula formed around the dying star, a beautiful shell of glowing gas illuminated by the hot, exposed core. And here's something crucial. Some of that expelled material didn't escape the system. Some of it fell onto Sirius A. When one star in a binary system loses mass, some of that material can be captured by the gravitational field of the companion star. This process is called mass transfer, and it can significantly alter the properties of the receiving star. Sirius A may have accreted material from the dying giant, gaining mass and possibly being enriched with heavier elements that were forged in the interior of the more massive star. This accretion could have altered Sirius A's composition, its rotation rate, and possibly even its luminosity. The Sirius A we see today might not be exactly the same star it was before the mass transfer event. It may have been modified, enhanced even, by material donated from its dying companion. This phenomenon, where the originally less massive star ends up as the more prominent member of the system after the more massive star dies, is common in binary star evolution. Astronomers call it the Algol paradox, named after the binary star system Algol in the constellation Perseus. In Algol, the less massive star is the more evolved one, which seems to violate the rule that more massive stars evolve faster. The resolution is that the currently less massive star was originally the more massive one, but lost most of its mass to its companion during a mass transfer phase. The Sirius system tells the same story. Sirius B was once the heavyweight champion of this pair. It lived fast, died young, and in the process, it may have boosted its surviving companion, handing off material that made Sirius A slightly more massive and more luminous than it would otherwise have been. After the planetary nebula phase ended and the expelled material dissipated into space, the system settled into its current configuration. One bright main sequence star, accompanied by one cooling white dwarf, orbiting their common center of mass every 50 years. The violence of the past is invisible now. The planetary nebula is long gone, dispersed and diluted beyond detection. The mass transfer that may have altered Sirius A left no obvious scar. All that remains as evidence of the system's turbulent history is Sirius B itself, a tiny, super-dense remnant that whispers of a star that once outshone its companion and now orbits silently in its shadow. This brings us to a broader point that changes how you should think about the night sky. Sirius is not unusual in being a binary system. In fact, the majority of stars similar to the Sun or more massive exist in binary or multiple star systems. When you look up at the stars, many of the single points of light you see are actually two or more stars orbiting each other, unresolved by your eyes into separate objects. The night sky is full of hidden partnerships. Procyon, the bright star in the constellation Canis Minor, is another binary system remarkably similar to Sirius. Procyon A is a main sequence star about 1.5 times the mass of the Sun. Procyon B is a white dwarf with about 0.6 solar masses. The parallels with Sirius are striking. A bright main sequence star paired with the dead remnant of a companion that was once the more massive member. The system evolved through the same process. The originally heavier star died first, shed its outer layers, and left behind a white dwarf. The surviving star continues to burn while its companion slowly cools. Alpha Centauri, the nearest star system to our own, is a triple system. Alpha Centauri A is a star very similar to the Sun. Alpha Centauri B is a slightly smaller and cooler star. Proxima Centauri, the closest individual star to Earth, is a tiny red dwarf gravitationally bound to the other two and orbiting at a much greater distance. Even our nearest stellar neighbour is not a single star, but a complex multi-star system. Algol, which I mentioned earlier, is a triple system containing an eclipsing binary where one star periodically passes in front of the other as seen from Earth, causing regular dips in brightness that have been noticed for centuries. Ancient Arabic astronomers called Algol the demon star because of its mysterious blinking, never suspecting that the dimming was caused by one star eclipsing another. The truth behind the demon's wink wasn't understood until the 18th century, and the full three-body nature of the system wasn't confirmed until even later. What seemed supernatural turned out to be orbital mechanics. What appeared to be one erratic star turned out to be three stars in a complex gravitational dance. Mizar, the middle star in the handle of the Big Dipper, is actually a quadruple star system. 4 stars orbiting in pairs, the pairs themselves orbiting each other. And nearby in the sky, a fainter star called Alcor is also gravitationally associated with the system, making it possibly a sextuple system. 6 stars masquerading as 1 or 2 points of light. The first person to resolve Mizar into 2 separate stars through a telescope did so in the 17th century. It was one of the earliest visual binary discoveries in the history of astronomy. But it took centuries more to reveal the full complexity lurking within that single point of light. The universe is full of these hidden multiplicities. Studies estimate that roughly half of all sun-like stars have at least one companion star. For more massive stars, the fraction is even higher. Perhaps 70% or more of stars similar to Sirius A's mass exist in binary or multiple systems. What you see as a single point of light in the night sky is, more often than not, 2 or more stars locked in a gravitational embrace, their individual identities merged by the vast distances that reduce them to a single unresolved dot. And many of these systems contain objects that are just as strange as Sirius B. White dwarfs are common. They're the most common type of stellar remnant in the galaxy. Every star with a mass between roughly 0.8 and 8 solar masses will eventually become a white dwarf. That includes the Sun. In about 5 billion years, the Sun will exhaust its hydrogen, swell into a red giant, shed its outer layers, and collapse into a white dwarf roughly the size of Earth. If any of the planets survive this process, the remnant solar system will look hauntingly similar to the Sirius system today. A tiny, incredibly dense stellar corpse surrounded by whatever remains of its former planetary system, slowly cooling in the darkness for billions of years. The Milky Way contains an estimated 10 billion white dwarfs. 10 billion. Most are invisible to us, too faint to detect without powerful telescopes. They're scattered throughout the galaxy, the accumulated remains of stars that lived and died over the past 13 billion years. Each one was once a functioning star, producing light and heat and energy. Now they're cooling embers, slowly radiating away the last of their stored thermal energy. And many of them, like Sirius B, orbit living stars, hidden in their companion's glare, detectable only through their gravitational influence or through observations at wavelengths where the white dwarf is relatively brighter than its companion. This means that the night sky is not what it appears to be. It looks like a collection of individual bright points scattered across a dark background. Simple, static, peaceful. But behind that simple appearance lies a reality of extraordinary complexity. Many of those points are multiple star systems. Some contain dead stars. Some contain stars that are actively exchanging material. Some contain orbits so close that the stars are nearly touching, distorted into teardrop shapes by each other's gravity. Some are slowly spiraling inward, destined to merge in spectacular collisions millions of years from now. The sky is a graveyard and a nursery and a dance floor all at once, and most of the action is invisible to the naked eye. Sirius is a perfect example of this hidden complexity. For thousands of years, every human who looked up at the night sky saw Sirius as one star, the brightest star, a beacon, a landmark. Ancient Egyptians built their calendar around it. The Greeks named it the dog star. The Romans blamed the summer heat on it. Millions of people across hundreds of generations looked at that same point of light and never suspected that they were looking at two objects. One blazing with the energy of nuclear fusion. The other a collapsed stellar corpse, barely the size of a planet, carrying the mass of an entire star in a volume you could almost reach out and wrap your arms around relative to its mass. The duality was invisible. The complexity was hidden. The truth was stranger than anyone imagined. And that's the real lesson of Sirius. The universe is not what it looks like at first glance. The simplest observations often conceal the most surprising realities. A bright point of light turns out to be a binary system with a violent evolutionary history. A steady, unblinking star turns out to be a partnership between a living star and a dead one, orbiting each other in a 50-year waltz that has been ongoing for longer than human civilization has existed. Sirius also teaches us something about the relationship between familiarity and understanding. Sirius is one of the most familiar objects in the night sky. It's been observed by every culture that has ever looked upward. It's one of the first stars most people learned to identify. And yet, truly understanding what Sirius is requires knowledge of stellar physics, quantum mechanics, gravitational dynamics, spectroscopy, and the life cycles of stars. The most familiar object in the sky required 2 centuries of scientific progress to decode. From Friedrich Bessel's detection of the wobble in 1844, to Alvin Graham Clark's visual confirmation in 1862, to the spectroscopic measurements of the early 20th century, to the quantum mechanical explanations of the 1920s and 30s, each generation of scientists peeled back another layer of the mystery. Each discovery revealed something stranger and more wonderful than what came before. The Sirius system also reminds us that nothing in the universe is permanent. The system we see today is a snapshot, a moment frozen in cosmic time. It hasn't always looked this way, and it won't always look this way in the future. Hundreds of millions of years ago, Sirius B was the brighter star. Millions of years ago, the system was surrounded by a glowing planetary nebula. Today, Sirius A dominates while Sirius B fades. Hundreds of millions of years from now, Sirius A itself will exhaust its fuel, swell into a red giant, shed its outer layers, and collapse into its own white dwarf. The system will then contain 2 white dwarfs, 2 stellar corpses, slowly cooling together in the darkness, 2 ghosts orbiting each other for trillions of years as the universe grows colder and emptier around them. That double white dwarf future is worth pausing on, because it reveals something profound about the ultimate fate of stellar systems. When Sirius A dies, the mass it ejects during its red giant phase will change the dynamics of the orbit. The system will lose mass, and that mass loss will cause the orbit to widen. The 2 white dwarfs will end up farther apart than Sirius A and Sirius B are today, circling each other more slowly in a wider, more languid orbit. Sirius A's white dwarf will be freshly formed, still glowing blue-white with residual heat. Sirius B's white dwarf will have been cooling for over 1 billion years by then, dimmer and redder, further along in its slow fade toward darkness. 1 ghost brighter, 1 ghost dimmer, but both beyond the reach of any nuclear energy source, both running on stored heat alone, both destined to cool and cool and cool until, trillions of years from now, they radiate so little energy that they become essentially invisible. Dark objects in a dark universe, still orbiting, still bound by gravity, still together, but producing no light that any telescope could ever detect. That future is unimaginably distant by human standards. Trillions of years is a span of time so vast that it makes the entire current age of the universe seem like the blink of an eye. But for white dwarfs, time is all they have. They don't explode, they don't collapse further as long as they stay below the Chandrasekhar limit. They just cool. Slowly, patiently, endlessly. The final fate of the Sirius system is to become 2 small, dim, cooling remnants drifting through a galaxy that itself will have changed beyond recognition. But that's the far future. Right now, tonight, Sirius is alive. Sirius A is burning hydrogen in its core at a furious rate, pouring out 25 times the sun's luminosity in brilliant blue-white light. Sirius B is glowing faintly with the residual heat of a former life, its surface still blazing at 25,000 Kelvin, even though no fusion powers it. The 2 are separated by billions of kilometers, and connected by gravity, tracing their slow elliptical paths around a shared center of mass, just as they've been doing since before the first fish crawled onto land on Earth. So the next time you step outside on a clear winter evening and you look toward the southeast, below and to the left of Orion's belt, and you see that brilliant star blazing white against the darkness, I want you to remember everything we've talked about tonight. Remember that the light hitting your eyes left that system 8.6 years ago and has been traveling through the void of interstellar space at 300,000 kilometers per second ever since. Remember that the brightness you see is not a simple thing. It's the product of genuine luminosity, a star 25 times more powerful than the sun, combined with remarkable proximity, one of the closest star systems to Earth, filtered through the relentless mathematics of the inverse square law. Remember that Sirius A is a real physical object, a ball of plasma nearly twice the mass of the sun, with a surface temperature approaching 10,000 Kelvin, a radius 1.71 times the sun's radius, and a core where nuclear fusion converts millions of tons of hydrogen into helium every second. Remember that it sits on the main sequence of the Hertzsprung-Russell diagram. in the prime of its life, but with a lifespan measured in the hundreds of millions of years, rather than the billions that our sun enjoys. And remember what you can't see. Remember Sirius B, that tiny, unimaginably dense white dwarf, roughly the size of Earth but carrying the mass of a star. An object where a teaspoon of material weighs 8.5 tons. An object held together not by heat or chemical bonds, but by the quantum mechanical pressure of electrons refusing to share the same quantum state. Remember that this object was once a living star, a blazing blue giant that outshone Sirius A, that burned through its fuel in a cosmic eye blink, swelled into a red giant, shed its outer layers, and collapsed into the dense remnant that orbits Sirius A today, invisible to the naked eye, detectable only through the subtle gravitational wobble it imposes on its companion. The brightest star in the night sky is not what it appears to be. It's stranger. It's more complex. It has a history written in physics and gravity and quantum mechanics. It's a system, not a star. A partnership between the living and the dead, the blazing and the fading, the visible and the hidden. And this is true of so much of the universe. What we see is the surface, the obvious, the simple picture. But beneath that surface, when we look more carefully, when we measure more precisely, when we apply the tools of physics and mathematics and patient observation, the reality is always richer, always more layered, always more surprising than we expected. Every star has a story. Every point of light in the night sky is more than it appears. The universe rewards curiosity. It rewards attention. It rewards the willingness to look beyond the obvious and ask what's really going on. Sirius is the brightest star in the sky. And it's also a reminder that the universe is always stranger than it looks. That the most familiar things often hold the deepest secrets. That even something you've seen 1,000 times can surprise you when you finally understand what you're actually looking at. Look up tonight. Find that brilliant white light in the winter sky, and know that you're seeing two stars, not one. One alive, one dead, both extraordinary, both bound together by gravity across the vast emptiness of space, orbiting in silence, telling a story that took 2 centuries of human genius to decipher, a story written in light and gravity and the strange quantum physics of matter crushed beyond recognition. The brightest star in the sky is keeping a secret. And now you know what it is. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean more than you know. It helps me keep making these deep explorations of the cosmos, one star at a time. Sleep well tonight under the stars, and may you never look at Sirius the same way again. Good night.